So in the picture that we've got here, it's just the same graph. The notation we use for path analyses are pretty much aligned with the notation I've been introducing for SEM. A single-headed or a directional arrow indicates a regression path. Now, notice I have straight in parentheses because you will see complex graphs where you can't have a straight arrow where they don't all intersect with each other. So it does not actually need to be straight. It only has to have one head. A double-headed arrow or bidirectional arrow, generally they are curved. Okay, again, they don't have to be, and those are meant to capture correlations or covariances depending on the context. Now again, I think I said this already, but generally when we do path analysis, we almost always use standardized regressions, which means a covariance between two variables is actually, once you standardize a covariance, you just get the correlation. And then last but not least, the only thing to note is what's missing. Missing paths are technically there, they're just zero. And it turns out that from the matrix perspective, if you remember yesterday when I was drawing the equations, I kind of I set the equations up in a way where I could add the zeros easily. That's why the matrix captures all of those zeros. So while we see certain numbers present, there are just as many numbers that are actually missing. Oh, sorry, that's not. There are the numbers we see are indicated. It's important to recognize that what's not drawn is still there. It's actually a zero. The matrix actually picks up that. In some models, there are many more zeros than not. And the nice aspect about structural equation modeling is it gives us tools to say, look, maybe one of those zeros shouldn't have been zero. And that can be useful. Before I go any further, let me see any questions so far on this. I know that a number of you have had some form of path analysis before. I'm not sure at what level or depth it was.
We were all in the same class.
Yeah.
So,
Okay, so it's all familiar so far?
Yeah.
Okay.
Can I just ask, how are
Of
you
course.
supposed to draw gamma? Like, is it a Y?
The
Or
way-
is it like-
Good question. Here's how I draw it.
Is
I
it-
draw it as a bit of an upside down curly Q when I draw it.
Okay.
So I draw my gamma like that, sort of like an upside down fish.
Okay.
And then eta, the other one is, I always draw eta with a long tail. And then mu is the other one we see a lot. It's like the tail is like an
Okay.
M, the U with the extra long. Let's see, and then the two, so then psi is the triple squiggle, zeta is the long double squiggle. We'll see that one as well. Let's see, any other fancy ones that we need to worry about? I think those are the main. And again, that's how I draw it. When it prints, it actually, it does look like a Y when the way and that's partially because it's italicized there. So.
Thank
I already said that the endogenous variables, when you have a relationship between an endogenous, we call that beta, whereas everything coming from a exogenous variable is labeled as a gamma. Now, under almost all circumstances, this is very important. Gamma 1, 2 and gamma 2, 1 are not the same number, but almost always in the matrices we're looking at, they are, because covariance matrices are symmetric. So that is one important thing to note. All right, so the goal in path analysis, the goal is to explain the variation in the dependent variables. That's what we want to do. If we have a good model, that's what it's supposed to do. The more variation for the dependent variables that we explain, the better. In all practical purposes, that's the R squared that we introduced, and I belabored a bit from the first lecture. Path analysis also then assesses the model by comparing covariances among the model variables. In particular, the closer the predicted covariance from the model to the observed covariance, the better. This is the first big change we see, because when we assessed model fit before, we were asking how well does each point get close to its actually predicted point. This is not talking about the points anymore. I'm not talking about individuals' responses. I'm talking about the correlations across everybody who I have collected data on. So that is the first. This is, if there's a way to highlight this as really, really important, I probably should do that. I would do it, except if I made everything all flashy and glowing and blinking, everyone gets freaked out and I get nasty comments in the comment bar at the bottom of YouTube. So this is the important part, because this is where we're beginning that transition from how we think about ordinary least squares and quote unquote assessing model fit to thinking about the matrix. Now, this is important. If you have 10,000 people responding to a survey with only 8 variables, it seems strange, but you only have, according to this rule here, this aspect, there's only 8 by 8 variables, 8 by 8 variance covariance values that are important. And technically some of them are repeated because it's a symmetric matrix. So technically it's 8 times, so it would be 8 times 7 divided by 2. So there's only 56 divided by 2, 27, 26, 20, 56, 28, 28. There's actually only 28 distinct covariances between those 8 variables. Despite the fact that I collected data from 10,000 people, I'm actually only working with 28 pieces of information. And that is a big mental transition to make. Now, when you have 70 to 80 variables, well, you've actually got lots and lots of variables to work with. You still need large sample sizes. So the analogy is not that dissimilar. Model variation is the way so model variation for the dependent variables, we want to explain that a lot. That's how we begin the estimation process. Once we have that, then we ask if the model fits, and that's by looking at the covariance matrix. That's the model assessment part. So path analysis on its own really does sit halfway between what we know about ordinary least squares and where we're going with structural equation or latent variable analysis. Okay. So how do we get these model predicted values? This is probably the part that, this is usually the part that's not explored in most times when path analysis is introduced. So the predicted values are, I have it listed as covariance correlation. Technically, if we've obtained standardized coefficients, if we've obtained standardized regression coefficients, then that we're all looking at just correlations. And if we haven't, if it's unstandardized, then it would be covariances. The key is we find our values by summing the values we get from separate paths. The multiple coefficients along the paths get multiplied together, and you have to find all of the quote-unquote legal paths that actually exist. All right, now we're going to practice this, but let me clarify. What are the rules? The rules are you can pass through a variable at most once. Rule number 1. Rule number 2, you can only switch from going backward to forward at most once. Okay. Notice you can't switch from forward to backward. So if I'm moving forward, I can't turn around and go backwards. But I can switch from backward to forward. And at most, I can cross a single double-headed arrow on a path. Okay. So let me go back to the slide here, and let's look at a few of these. All right, so I can talk about the path. If I want to know, if I want to get from, well, let's keep it. No, there's no way to keep this easy. So if I want to look from psi1 to, no, I can keep these. Let's go from psi1 to eta 1. How can I get from psi1 to eta 1? Well, obviously, the most direct version is just along gamma 1, 1. Let me keep totality of that. So we've got gamma 1, 1. Now, to get from here to here, or vice versa from here to here, I'm allowed to move backwards, but once I start moving forwards, I can't. So I can't go from here to there. Well, I can, but then I'm done, because I can only hit a variable once. How about I go from psi1 along the curved path to psi2? Then I can go from psi2 to eta 1. Oh, I just realized this isn't labeled. That should be labeled with an R. So that path would be along R, which I'll label R21, the correlation between psi1 and 2. That's the correlation value times gamma 2, 1.
Gamma 1, 2.
Gamma, oh, thank you, yes, top one, thank you. Yeah, gamma 1, 2. All right, so again, let me trace up on here. So this is going along R21, which isn't labeled here, and then gamma 1, 2. So that gets me from psi1 to eta 1, and those are actually the only two paths that I can take. If I move forward here, I have to move backwards, which I'm not allowed to do, and those are really the only options I have to leave psi1. So I've pretty much exhausted every way that I can get from psi1 to eta 1. So if I add these values together, this should give me the correlation between psi1 and eta 1. Okay, so far so good. Because now we're going to get messy. Now we're going to go psi1 to eta 2. Okay, so how can I go from psi1 to eta 2? All right. We've got a direct path, which is gamma 2, 1. There's my direct path.
Gamma 1, 1 to beta 2, 1.
Gamma 1, 1 to beta 2, 1. And that would be a indirect path. So gamma 1, 1 to beta 2, 1 is indirect.
And those are multiplied?
When you multiply along the path, and then you add everything in the path, all your paths separately. Okay, how else can we get from psi1? R times, which was it, gamma 2, 2? Gamma 2, 2. So we go from psi1 to psi2 along the correlation, psi2 to eta 2. Okay. And then we technically have one more path.
R gamma 1 to beta 2, 1?
Yep, from psi1 along the correlation to psi2 up to the mediating value, so along gamma 1, 2, and then down beta 2, 1. So that would be R21, gamma 1, 2, beta 2. This would give us the correlation for psi1 and eta 2. If I add, so in this case so this is what we call path decomposition. So we decomposed our paths, and these are all the possible paths that can connect, legal paths, that can connect us from psi1 to eta 2. On each separate path, we multiply the coefficients, standardized coefficients or correlations, and that gives us the amount of influence coming from that path. And then we add those all together.